Good morning. Yeah, it's working. Perfect.
Hello. Yeah, I think it works.
I prefer. So, welcome everyone to this third edition of the Bridging European Science event. It's really a pleasure to be here, especially this event has been a bit trouble to do during this pandemic and COVID situation. But I'm really excited to be here, especially because we started in 2016 in Lund with the first edition. I'm happy to see Eva here, that she also was part of that. And then we went to 2018 to the second edition in Berlin. And then we thought, okay, the third edition should be in Copenhagen. Yes, 2 years later. Yes, 2020. Yes. And then we had a surprise. We had this event planned for April 2020. So we were ready. All the speakers were confirmed. The venue was this one. Everything was ready. And we had that situation that we had to postpone it. The idea of this event comes from the Øresund area with this bridge that joins Denmark and Sweden. But also there is the Øresund Science Region, which has a focus of having science across borders and bring innovation, research and development without thinking whether you are in Denmark or Sweden. And that's why we have called it Bridging European Science. And it comes from these associations of Spanish researchers all over the world, but specifically in the Nordic countries. In this case, we have Denmark, Sweden, and Norway. And of course, we are all Spanish, so Spain is also here. The main objective of this event is to talk about the latest innovations of research all over the world, but with a focus on what's been more important for the Nordic countries lately. As I said, this has been a bit of troubleshooting. We have been 3 presidents of the association in Denmark who has been organizing this event. I started in 2020 saying, yes, I will do this, and that's my last thing I will do as president. And there was no choice but to postpone it. And then in April we said, September, we'll do it in September. Yes, this will be over by then. Surprise. So then Daniel Gómez Cabello, he was the president later, and said, we'll do it April 21, a year later, it should be over. April 21, Denmark is in full lockdown, nothing could be done. So then Enrique took over, and then it was okay, now we do it in August, and that's it, no matter what. So we're really excited to be here. Of course, nothing of this could have been done without our awesome group of volunteers. You have met them in the registration and everywhere, but it's always nice that you see there's Blanca, Sandra, Christina, and Martin. They have been taking care of absolutely everything. And of course, our partners in crime from Sweden and Norway, which have made it possible and have this international collaboration across countries. Before I finish, I would like to say that the next one will be in Norway, 2023, hopefully COVID-free. That should be possible. And we are also thinking maybe we can go in winter and have some of these nice skies, but we'll see about that. Before I continue, I would just like to say a few details. This is a live stream event, not only for the speakers, but also for the audience. So keep your smiles up. You are going to be on YouTube. I also would like to thank the sponsors. We have got the support and the collaboration from the Ramon Areces Foundation from Spain, from the Embassy of Spain in Denmark, and from the Foundation for Science from Spain. That has been our major supporters, have made everything possible. Finally, the event will be in English. There will be some remarks in Spanish to start with, but the rest of the event is all in English. Please keep your phones in silence, and welcome. To continue with the opening, we have the representative from the Spanish Embassy in Denmark, Manuel Martinez Camayo, who will give some words.
Thank you very much. Welcome, everybody. Science is progress, and a new general awareness about this fact has emerged in the context of the present global pandemic. Many lessons have been drawn from this critical situation. Therefore, we can count today on a new understanding among governments, institutions, media, and the general public about the utmost importance of supporting science, research, and innovation, and putting together financial resources and talent. I can assure that the Spanish administration is fully engaged in this effort. Our Ministry of Foreign Affairs and Cooperation is trying to promote the efforts of our younger generations of scientists and researchers abroad. Through the so-called scientific diplomacy, our aim is to create synergies, to spread networks, and to support Spanish scientists working and researching in different countries. This is one of the purposes of this meeting. The Spanish embassies in the 3 Nordic countries are very happy to collaborate through their cultural sections in the organization of this symposium, Bridging European Science. Let me address our warmest congratulations to the different associations of scientists in the Nordic countries as promoters of the BES initiative, and in particular to the organizers of this 3rd edition, which we are gladly hosting in Copenhagen. I would like also to congratulate and thank all the professionals who are attending the event this weekend, as well as the speakers and moderators who will lead us through this edition's program in the relevant topics of space, medicine, and sustainability. I would like to address a special word of welcome to astrophysicist Begoña Villa, who has traveled from Washington, D.C. Fostering scientific interactions between the public, private sectors, and countries to make possible ideas to sparkle, to cooperate in order to find common solutions to today's global challenges. Those are the goals which bring us here together. So allow me to wish you a very fruitful weekend, and let Copenhagen inspire you. Thank you very much.
Now to continue, we'll have some welcome words from Pilar Ayuda, who is the president from the association in Norway.
Hi everybody, I'm Pilar Ayuda Duran, and I'm, as she said, I'm the president of the Spanish Researchers Association in Norway. We are the youngest association here. We were born just in 2019, and we have members spread all around Norway, but mainly in Oslo. We are most of us concentrated there. And today I just want to say thank you to everybody who came here. It's been a long road until we reached this point. And I just want to say that we are very happy to be here. We want to thank the Ramon Areces Foundation, CET, and the embassies. Especially from my side, I want to thank the Spanish embassy in Norway, but all of them for their support. And we just hope that you enjoy the event, and thank you very much for coming.
We continue now with Francisco Villaplana, who's the president from the association in Sweden.
Thank you, Paula. Good morning, everyone. My name is Francisco Villaplana. I am the president of the Association of Spanish Scientists in Sweden. And it's a pleasure for me to be here today, finally, after all this road of sweat and tears. This association was founded in 2014, and we have around between 180 and 200 members. We're mainly based in the areas of Stockholm, Uppsala, and also in Skåne, in Lund. But now we're very happy that we're extending to have a new node in Gothenburg, which makes us very happy because we can actually cover most of our territory and hopefully reach our community. As Pilar was saying, our goal is to engage the Spanish community of scientists in Sweden, and that's what we do and what we are so happy about. I just wanted to thank, I mean, it's a bit of repeating, but first of all, I really wanted to thank our colleagues in Denmark, because, I mean, to put this event in these circumstances, it's a big amount of work, so thank you particularly to all of you here. It's fantastic. Then I also wanted to thank, of course, the Spanish Embassy in Sweden, and here we have our consul, Juan Villar. Thank you very much, because we feel your support in everything that we do. Of course, I have to thank the foundation, the FECIT, and also the Fundación Ramón Areces for all the help that they provide us, because that's why we can come here. And the last thing I really wanted to help is to thank our ambassador of ACES. He's a very special person for us, Eva Ortega Paino, who is coming here from Madrid. And as Paula was mentioning, she was one of the catalysts to have this Bridging European Sciences started. And I really hope you enjoy this event today. Thank you very much.
Finally, our own president, Enric Juan, from the association in Denmark.
Okay. Can you all hear me? I mean, I have this all set up. Okay. First of all, thank you very much. I'm like extremely nervous today. It's been a long road to get here, and I know that especially all the people next to me, they have suffered quite a bit all the preparation of this event. But without further ado, I'm just gonna say a few words, and I wanna raise a question. It's why are we here? We come from really different fields. We come from space, we come from sustainability, we come from medicine. We try to do our best always, but we have something in common, so we love science, right? And society needs science. The problem is that large part of the society doesn't know that they need science. And most of the times is because, I mean, we do our best, we do an amazing work, but sometimes we fail when we try to communicate the amazing work that we have done. So let's say the main target, the main purpose that bring us here is to try to bridge that gap and to try to do our best and try to show society and try to say, hey, we are doing this for all of you, and this is just to make a better society. So without further ado, just to say thank you to especially Spanish Embassy, FECIT, Fundación Ramón Areces, and all the amazing work from the voluntaries. And yeah, this will never be possible without them. So I think that was all that I wanted to say today. And let's just give pass to the next thing. We wanted to have here the presence of the science minister, also the director of FECIT. That it's not going to be possible, but we have to thank you them, because they sent some videos trying to give express some words. So just maybe if you allow me to try to browse a bit. Okay. Just to say for the people online that these videos, they are going to be in Spanish, but the whole event then will continue in English. So please hold on, and then can be a good exercise of try to learn some Spanish.
Hola, buenos días a todos y muchas gracias por invitarme como directora general de la FECIT a la tercera edición de este simposio organizado por las 3 asociaciones de investigadores españoles en el extranjero de los países nórdicos, Dinamarca, Suecia y Noruega. En primer lugar, quiero mandar un saludo muy cariñoso a Román Oyarzún Marchesi, embajador español en Dinamarca, y también, por supuesto, a los responsables de las asociaciones Enric Juan, Francisco Villaplana y Pilar Ayuda. Os agradezco muchísimo vuestra motivación y el impulso para organizar este evento. En FECIT llevamos 20 años estimulando el interés y la curiosidad por las ciencias. Tenemos la misión de reforzar el vínculo entre ciencia y sociedad mediante acciones que promuevan la ciencia abierta, la ciencia inclusiva, la cultura, la educación científica, dando así respuesta a las necesidades y los retos que tiene el sistema español de ciencia, tecnología e innovación. Nuestro plan de actuación se articula en torno a 6 objetivos estratégicos. Uno de ellos es el de promover la ciencia global. Se trata, pues, de un área estratégica que se alinea con la Estrategia Española de Ciencia, Tecnología e Innovación, diseñada por el Ministerio de Ciencia e Innovación, cuyo eje número 14 hace referencia precisamente a promover el compromiso de la sociedad española con la I+D+I. A través de nuestro plan de actuación de la FECIT queremos dar un impulso social al sistema español de ciencia, tecnología e innovación para que éste cuente con el respaldo de la sociedad, una sociedad formada y comprometida con la ciencia, y apoyar así las políticas del Ministerio de Ciencia e Innovación del Gobierno de España en materia de ciencia abierta, internacional y políticas de género. En el marco del objetivo estratégico al que me acabo de referir, FECIT colabora con las asociaciones de científicos e investigadores españoles en el exterior en actividades de promoción de oportunidades para hacer ciencia en España y también de visibilización de las asociaciones en España y en los países donde operan. Por eso, hoy me gustaría destacar especialmente los mecanismos de colaboración y de comunicación que desde la Fundación Española para la Ciencia y la Tecnología hemos establecido a lo largo de estos años con estas asociaciones. La ciencia española hace gala de una importante consolidación y goza de prestigio internacional, y los científicos españoles en el mundo son una muestra de ello. La Fundación, la FECIT, junto al Ministerio de Ciencia e Innovación, ha impulsado diferentes iniciativas para colaborar con estas asociaciones, que son una voz fundamental en el sistema. A día de hoy, con 18 asociaciones constituidas y con más de 4.000 científicos españoles afiliados, FECIT ha firmado 12 convenios de colaboración con varias asociaciones de científicos españoles en el exterior, así como con RAICEX, su federación, siendo un área estratégica para FECIT desde el año 2012. Precisamente con RAICEX pusimos en marcha en 2020 el programa Rebeca, un programa de mentorazgo para conectar a jóvenes investigadores con profesionales fuera del sector académico, con gran éxito de participación tanto por parte de mentores como de investigadores e investigadoras que quieren explorar otros caminos en su carrera profesional. El papel de las comunidades de investigadores españoles en el exterior es muy importante para favorecer esa relación entre estos y el sistema español de ciencia y tecnología, clave para el futuro de nuestro país. Las comunidades tienen un gran espíritu colaborativo. FECIT es una institución de prestigio en mecanismos de conexión ciencia y sociedad, y además somos una entidad transversal, ya que tenemos acceso a la comunidad científica, también a la comunidad universitaria y en todas las disciplinas. En ese sentido, impulsamos la movilidad y la empleabilidad de los investigadores. Somos coordinadores nacionales de la Red Española de Euraccess, una iniciativa apoyada por la Comisión Europea que da información y servicios de apoyo profesional a investigadores en Europa. A través de la sección Science in Spain del portal Euraccess Spain, damos difusión a las oportunidades de contratación de investigadores de instituciones de investigación de España. Pero también editamos cada año la publicación Researcher Career Path in Spain at a Glance. Se trata, en este caso, de un completo diagrama actualizado de las distintas etapas de la carrera investigadora en el que se identifican las distintas ayudas que se pueden solicitar en cada momento. Además, el documento contiene los enlaces en los que se puede ampliar información sobre cada una de las convocatorias. Quiero acabar mi intervención con mi más sincera felicitación por la celebración de esta tercera reunión, que constituye una señal inequívoca del liderazgo profesional y del poderoso precedente que significa esto para el futuro. Creo que este encuentro es una buenísima ocasión para establecer puentes de comunicación efectivos con las comunidades de investigadores españolas en el exterior. Deseo de todo corazón que las reuniones y las mesas redondas que vais a tener durante estos 2 días sean muy fructíferas.
Let's go. Maybe you can give me 1 second because we have a technical thing that we have to cover. Okay, maybe. Yes, thank you. Yes, finally.
One of our speakers is online and waiting.
Yeah.
Our own
Sorry?
Spanish astronaut.
Yeah, but how can I do just to wait? Okay. Okay. Hi, Sir Pedro Duque.
Hola, buenas.
Buenas. Will you give us a few minutes? You know, we are a bit late. Sorry.
Okay,
I
I'll
will
stay here.
Okay, I will introduce you just in a few minutes. Thank you. These are the things that of the life. Okay, you try to do your best to make the program to stay on schedule, and then everything goes off right. So.
Hola, buenos días a todos
No.
y muchas gracias por invitarme como director.
Speaking about. Okay.
Buenos días. Os agradezco la invitación a participar en esta tercera edición del Bridging European Science y os felicito por la organización, que sin duda refuerza la relación de España con los países nórdicos, con sus universidades, sus empresas y también con el sector público. Uno de mis principales compromisos, como dije en mi toma de posesión, es que los investigadores e investigadoras vais a ser interlocutores prioritarios para el Ministerio. Y los científicos y científicas que estáis fuera sois fundamentales. El objetivo es que entre todos podamos generar oportunidades para que España pueda aprovechar vuestro talento y dedicación si así lo queréis, que tengáis aquí el reconocimiento y las condiciones necesarias para desarrollar vuestro trabajo. El momento que vivimos es muy propicio para ello. La sociedad en su conjunto ha entendido mejor que en cualquier otro momento que la investigación y la innovación tienen como finalidad mejorar nuestras vidas, incluso salvarlas. La convicción de este Gobierno en este sentido es firme y se ha plasmado en el Plan Europeo de Recuperación, Transformación y Resiliencia, que ha situado a la ciencia y a la innovación como áreas prioritarias. Hay datos contundentes que sostienen que esta vez sí, la I+D+I es importante. El Ministerio de Ciencia e Innovación ha aumentado un 60% su presupuesto y el año que viene lo volveremos a incrementar. Hemos publicado la oferta de empleo público más grande de la historia y una parte muy importante de esta es para personal que trabaja en áreas de ciencia y tecnología. Y la semana pasada se publicaron los datos de afiliación a la Seguridad Social, datos muy positivos, entre los que destaca la afiliación en el sector I+D, que del año 2019 al año 2021 ha sido el segundo sector que más ha crecido. Son todos ellos datos que sin duda invitan al optimismo y que nos permiten asegurar que estamos en el camino correcto. Ese apoyo del sector público y la inyección inicial de fondos se ha de mantener para convertir la ciencia en el pilar de la salida de esta crisis. Para lograrlo, seguiremos impulsando el Pacto por la Ciencia y la Innovación, que tiene como objetivos incrementar la inversión en ciencia hasta alcanzar el 3% de nuestro PIB en 2030 y hacer la carrera científica más atractiva y predecible. Como firmantes de este pacto, sé que cuento con vuestro apoyo para que sea una realidad. De la misma manera, podéis contar con mi apoyo, con el del Ministerio y el de los organismos dependientes. Uno de los grandes dramas de nuestro país en la última década ha sido la llamada fuga de cerebros, por lo que vamos a poner las medidas necesarias para revertirla. Vuestra experiencia internacional os confiere una visión global muy enriquecedora que nos gustaría aprovechar para poder mejorar, que es en definitiva nuestra principal aspiración. Y en esa mejora, conseguir un sistema de ciencia, tecnología e innovación atractivo que nos permita atraer talento, tanto el vuestro, españoles en el exterior, como el de otros científicos extranjeros que quieran desarrollar su carrera en España. Termino ya. Os emplazo a que trabajemos juntos y os deseo todo el éxito en este encuentro y en todos los que vengan. Muchas gracias.
So this has been our welcome. Doesn't matter. And starting, so now we are ready for the most exciting and fun part, and that's the first session to talk about space. I'm not a space researcher at all, but I'm looking forward to hear all those things and hopefully understand a bit more what comes in the news about it. This session is going to be moderated by Enric Juan, who actually works in space, so he will present the next speakers.
Hi again. I really feel like a kid right now because I'm gonna introduce and moderate a blog which is about the space. I think it's an extremely interesting topic, and we are gonna kick off the blog with a short presentation from someone that I think needs no introduction. So it's the only astronaut that we have in Spain. It's one of our main representatives in science abroad, and I don't want to say anything else because let him just to make the presentation. Okay. Hi.
Hello.
Hi, Pedro Duque. Are you there? Okay.
Yes, I'm tempted to do a fun communications check protocol like we do from space station, but
sorry for the technical problems, but
yeah, conference station. Do you read?
I will leave you the floor. Okay, so it's all yours, and I'm really looking forward to hear you.
Okay, well, good morning. I don't see anybody of the audience. I suppose most of the audience is virtual anyway, and I'm really happy and grateful that you have invited me to give a very short talk to initiate the block about science or research in space. I've seen the topics. Obviously, these are the important topics. I didn't see, for example, science in microgravity as is done in the space station. Maybe somebody refers to it. As you know, I've just finished a 3-year stint as minister in charge of research and innovation in Spain. And therefore, well, I thought it would make sense to make a presentation about how do we frame space research in the context of all the rest of research and innovation as one of the areas that are distinct and that are somewhat different. I believe, and since I arrived as minister, I have been observing that the way that we do research in space, well, it is a little bit different or separate from the way we do research in all other areas for several reasons. For example, one is we group science in space by the means and apparatus that we use to make it, and not by the discipline. And that means that this is a different way of selecting space sciences. And when I went deep into, for example, in Spain, about the different disciplines and how you split funds amongst them, it is very difficult to match whether you're doing, for example, cardiology in itself or cardiology in space. Where do you put it? Because space normally has a special box. And that made me reflect on why do we do this? Obviously, because it has a big bearance on the money that we need to make science in space, and that therefore, and the technologies that in order to do science in space are all kind of common. So therefore, we group the science that we do in space in one single group, just because it needs a very special kind of apparatus that are in the forefront of technology. And that's what made me think, okay, well, why do we do this in space, and why don't we do it in other areas? Have the drive to do science be permanently linked to the drive to construct devices to do science that are of high technology. And this is what we call in space business the industry of science. This has been developed quite importantly in the case of space, and also in areas of high energy particles. And this is one of the things that I think makes space science stand out from the others, and probably give some hints to the others of how to proceed. The kind of tale that we tell for doing science in space is because we need, for example, a satellite with a gamma ray telescope orbiting at the L2 point between the Earth and the Moon, is it? Yes. Or is it L2 point with the Sun? L2 point with the Sun. For that reason, because the scientists need those data that the satellite is going to provide, then we develop all sorts of new technologies that put enormous burden on the inventiveness of engineers and technicians. By that, we spend a lot of money, but by spending this money, we develop technologies that are going to be useful for the economy as a whole. And this is maybe one of the aspects in which we consider somehow mentally science in space a little bit different than the others, in that we, from the very beginning, consider that our drive for science is going to provide high technology, which is going to be economically profitable. Why not everywhere else? And yes, I have introduced in these 3 years this mentality. I believe in the at least in Spain, and I have also tried very hard in the European Union itself, in order to promote one more reason to do science. And this is something that I have not seen in several other areas. Of course, there's very high technology being used in all other areas of science. The more sophisticated science, the more accurate and the more precise and the more distance, let's say that the highest precision possible of data that you need, and therefore you need devices that do it, and therefore you need an industry that provides those devices that didn't exist before and that develops technology. But it is not considered normally in other areas of science as a drive to make more science. And this could be one of the differences. And obviously, one other difference is that people see space quest, or the conquest of space as an adventure, and therefore many people get get very interested in the results of science done in space, maybe more than if it would have been, if that science knowledge would have been acquired in other ways. And we have to use it again as a drive to do more science. And therefore, I think that it is proper. One thing that happens quite often is that areas of science, in part, are driven towards space, for example, obviously astronomy. And by doing that, we drive more investments into science. I believe that, and I was speaking to students of the other day, and one of them asked me the question, how can we convince the government that science has a value and therefore they have to invest more in science and not so much in, well, all the rest of the things? And I believe there's a limit to this. It is impossible to convince a finance minister of any country that the value of the knowledge acquired by science has a very high value, and therefore they should spend lots of money on that and less on pensions or roads or healthcare. Of course, they understand that there's a value for the knowledge that is produced by science, but it doesn't go further. It doesn't go as far as we want to go into investment in science. And therefore, we need to be very mindful that we have to permanently link research, innovation, higher technology in the products that are sold by the companies of the, let's say, the area of the world that provided the research and then the innovation. And therefore, they have to be convinced that there's a cycle by which Minister of Finance gets money out of science. It is very important. We can't avoid this. We shouldn't detach ourselves from the world. And of course, 3 years in the government and in the Council of Ministers make you come to terms with reality very, very strongly. So what I would say is, listen to the types of science that are done in space. In all the other research areas that you carry out, all other disciplines, look for the two elements that will invite for higher investment in science. One would be the fascination that of course the population has, and therefore people in all countries have a certain drive to have their country be a little bit forward in space. But then the other is probably more important. That is the two ways in which you get economic value and benefit in a certain reasonable timetable from the science knowledge that you acquire. One is obviously that science provides new knowledge that provides new ideas for technology and better products, and the other is, and it is more immediate, it is shorter term most of the time, is by wanting and having a drive to do science of higher accuracy, you build with public investment devices to do science, and those devices are in the forefront of science and provide immediate benefit to the economy. So this, I think, we need to understand. If we start thinking as a minister of finance, then we will probably do much more science as a consequence. So, well, always think in your areas, wherever you are going, how a minister of finance thinks, and therefore we will probably be much better off doing research. Thank you.
Thank you. Thank you very much. We have enjoyed a lot the presentation. I'm gonna close the call, okay? So, but really thanks for participating in this event and giving us some time. Thank you. Bye bye.
Goodbye.
Okay, now we are gonna go through 4 different presentations about the space. After those presentations, we will have a short Q&A, so the audience will be able to make some questions, and then after that, we will proceed with a roundtable where we will try to discuss some of the most important and the hot topics about the space. Okay, so we are gonna start with yes. Let me go for the presentation. Let me introduce her. She is Begoña Vila. She is the systems lead systems engineer at NASA, and she is working in the development of the James Webb Space Telescope. So if you ever heard about the Hubble, this is kind of the the older brother, right? And she obtained her PhD in astrophysics at Manchester University, right? And then graduated in Spain. And I really need to read this because her research includes rotation curves of galaxies, nuclear galactic activity, and stellar abundances, observing both in optical and in radio wavelengths. So it's, I mean, to me it sounds like a fantasy, right? And just to finish with the presentation, she has received various awards, including the NASA Exceptional Public Achievement Medal in 2016, the Premio Wernenburger by the Xunta de Galicia in 2017, Galego del Año Award in 2018, and Top 10 Spanish Women Leader Abroad by Mujeres and Company in 2021. So with further ado, please, Begoña, the floor is yours.
Muchas gracias. Thank you, Enric, and thank you, all of you. It's a pleasure to be here with you today, and I'm going to tell you a little bit about the James Webb Space Telescope. I think looking at the sky, now we live in cities, so we don't see it so much, but in the olden days, that's what we had to tell us the change of the seasons, to travel, looking at the North Star, etc. And as we learn more with science, when the telescope was discovered, we were able to advance our knowledge, and we got to understand, unfortunately, the Earth is not the center of our solar system, and also that we don't live on a single galaxy. There are millions of them. So after developing this telescope, we were building some on the ground, and we have a lot of them to be able to look at the space. You can see there, the next thing we realize, of course, is that the Earth has an atmosphere that's going to affect the observations that we do on the ground. The atmosphere is going to move, it's going to do a little bit of blurring of any image you want to take. But also, as you can see here, this atmosphere protects us from some radiation, which is good for us because we need to live here, but it's not good to look at some of the wavelengths where the space gives us information. You can see there that from the ground, we can definitely look on the optical with some limitations, and we can look on the radio, which was used, for example, during the war, right? We have the big radio telescopes where we can collect then the radio signals that come from space. But we are not able to look any of the high energy emissions, and we cannot look in one particular wavelength we are going to talk today, which is the infrared, which is what James Webb is designed to do. And if you think about the objects in the sky, they are going to tell us about what they're doing and their lives in different wavelengths. So if we want to get a complete history of what's out there and how it evolves, we do need to take pictures in all of them. So in the middle of this century, not so long ago, we had the first satellite, the Sputnik, 1951, and that opened a new era. Again, we are learning, and we are now able to send satellites into space for many things. Of course, observing the Earth, our phones, GPS, lots of things we are familiar with that are part of our everyday life, but that before were not possible. But also be able to send these telescopes into space to be outside the atmosphere and then to look at all those other wavelengths. And as it was mentioned before, I think everybody is very familiar with Hubble. Hubble orbits the Earth about 600 kilometers around the Earth. And it was designed to look mainly as our eyes in the visible. And I think a lot of you know when it was first launched, it had a problem. Its mirror was slightly misaligned, so the images that it sent to the ground were fuzzy, so it needed some glasses to correct its problem. And to do this, because it orbits the Earth, there were missions with astronauts that could go and fix Hubble. And then also there were another 4 extra missions where they could go and install better instruments for observing. Hubble was designed, as any big telescope is, you have to have scientific goals in mind to get the agreement for the telescope to be built and get your budget. And in the case of Hubble, there are many great things that it did. But when you look at the universe in a different way, you always find things that you didn't know about, and it increases our knowledge. This is one of my favorite images from Hubble. This is a part of the sky, is about like a postage stamp. And if you look at it from the Earth, it's dark. There is nothing there. So, of course, we knew there was nothing there because we had looked at it from the ground, and it was part of our knowledge. But once Hubble was on orbit, there was a proposal to observe this part of the sky for a few days just to make sure there is nothing there. And this is the image that came down to the ground. And there is hundreds of objects there. They're all galaxies. So again, it taught us more than we knew, and it emphasized again how big this universe where we live is. So if we move then to the next, as was said, the brother of Hubble. This is the next telescope. It's called its successor. In reality, they are both going to be observing in parallel for a few years. Hubble, and there is no further funding to do any more repairs or to that telescope. Again, it's always a case of how much money you have and what can you fund. So Hubble will still last for a few more years, but then it will end. James Webb is launching at the end of this year, so I hope you'll all cheer and watch that when it happens. But for a few years, both will be observing together, which is going to be really good because James Webb is looking at the universe with different eyes on this infrared. And this is a top-level picture of what are the main components on James Webb. And the first thing we are going to notice on James Webb is that it has a part that's going to be very cold, which you can see is on the top. In there you can see the mirror. The light goes, here I have, okay. Yes, okay. So you have this big mirror. We are going to talk about that mirror a little bit more. The light from objects in the sky will come to this mirror. It will bounce back and go into this secondary mirror, and then it will bounce from that mirror and go through here. There is a tertiary mirror there, and all the instruments are packed in the back of the mirror. All this part of James Webb needs to be very cold. It needs to be very cold because we are going to observe in the infrared. The infrared, you can understand it as heat, and everything emits heat. So you're looking for images from things that are very faint, so you need to cool down everything else. Otherwise, you won't be able to detect them. So this part is going to be at 40 Kelvin, very close to absolute zero, about minus 233 centigrades. But on this side is where we have the electronics. The electronics don't like to be that cold, so we have to keep them warm. And then we also need to be able to cool down this part to those temperatures. And to do this, we use this sun shield, this a beach umbrella. So this is, if you were on the beach, this is the part that will always be on the shade. and on this side, it will always be facing the sun, the moon, etc. So this part here is going to be very hot as 88 centigrades. So one of the challenges for James Webb is not only that you're building something that's going to be operating so cold, but also that you have a hot and cold zone, and you don't want the heat from the hot to go to the other areas. So there is a lot of complexity for many of the team members involved to develop and have it ready. This is a model of the James Webb in real size. So you are going to notice the next challenge, which is that it's very big. It's the biggest telescope that we will have launched into space. And we are going to talk a little bit about why we did that and how are we able to launch it. Because you can clearly see you cannot fit this thing in a rocket. I mean, everybody can notice it. And this is a very small fraction of the team. And this is the center where I am based, Goddard Space Flight Center, just outside Washington, D.C. So let's compare Hubble and James Webb, which people are very familiar. So if Hubble was here with us, it would be as big as a school bus. If James Webb is here fully open, its sun shield is as large as a tennis court, and in height is about 4 floors high. So it's a much bigger size to launch into space. Having said that, James Webb is lighter than Hubble. When you launch something into space, there are certain requirements you have to meet. One of them is how much it weighs. The heavier, you need bigger rockets to be able to launch them. So you learn to use materials and processes that make what you are launching lighter. And of course, we have learned a lot. We can launch something bigger that weighs less than what we launched 20 years ago, which was the Hubble. The other important difference is the size of the mirror. So a bigger mirror allows you to collect more light. It's a bigger bucket, you're going to get more light, so you can see fainter things. And that's a great idea. You can see James Webb is much bigger, but you immediately run into a problem. I want a bigger mirror, but it has to fit inside this rocket. It cannot fit, so great idea. Let's make the mirror out of 18 smaller mirrors that I can fold. I'll fit it in, and then I'll open them and align them when they're in space. And this is a great idea, but then, of course, you have to make it reality, which, again, was another one of the challenges of the James Webb. And then the other thing is where it's going to be. Hubble, as we said, is around the Earth. We were able to service it. James Webb is going to be in one point that Pedro mentioned, L2, the Lagrange point number 2, which is about 1.5 million kilometers from the Earth, about 4 times the distance of the Moon. These are special points when you have 3 bodies, as a lot of you probably know, when you have 3 bodies in a space and you do the math to calculate the effect of the gravity for all of them, you will find 5 points where those gravities annul each other. So if you put something there, it's going to be pretty stable. So L2 is one of the positions. If we take the telescope there, it will mostly stay there. We have to do little corrections to that orbit. It's not 100% stable, but it's a good place. And also is away. The sun is on this side, and the Earth and the Moon. So we want to be cold. We want to be as far as possible from the sun. And then we can then put our sun shield pointing in this direction. So the sun shield is always going to be pointing to the sun and the moon, and we are going to be rotating like the Earth. So the mirrors and the instruments are always going to be cold, which is what we need. And then the other main difference, which we already talked, is where are we going to look into the sky, and we are going to go into the infrared, and we are going to talk a little bit more about what that means. Every time you design a big telescope, you're going to commit a lot of resources, a lot of money, and a lot of time. So it has to be an agreement. The scientists have to do a strong case why this telescope makes sense. So James Webb has 4 main themes, which were the drivers for its development. One of them is we are going to look back in time to the first stars and galaxies that were formed in the universe. Sometimes when you talk about looking back in time, what's going to happen is those first objects that were formed after the Big Bang, when they turn on, those stars emitted light. That light has been traveling through the galaxy, the universe is expanding. So what that does to the light is its wavelength is going to stretch. So if you saw on the previous picture, you can see here, when we are in the visible, this is the kind of wavelength that we have. Once we go to the infrared, it's not as noticeable here, but you see how the wavelength stretches. So if you stretch the wavelength, what you are doing is moving into the infrared. So if I want to detect that light from those objects from so long ago, 13.5 billion years, you need to take a picture over there. If I take a picture on the visible, I'm only going to collect the light of objects that are closer to me. They haven't traveled that far. So James Webb is going to look at those first objects that were formed. There are theories of how the formation of stars and galaxies occurred and how it evolved to the one where we live. This is an example of a galaxy where we live. We live in one of the arms of the galaxy. There are different types around us, different types of galaxies. We know about them and we have classified them. But when we start looking back in time, these are some pictures from Hubble. Hubble could look back in time a little bit, but not far enough. And you can already see these galaxies don't look like the one where we are now. So obviously there is a process of galaxy formation and evolution that we want to understand to see how we got where we are. James Webb is also going to look at the formation of stars and planets. Again, we know those first stars were much bigger. We know they only had helium and hydrogen because those were the only elements at that time in the universe. We know those stars exploded and formed all the other elements, which is how we are made. So again, James Webb is going to look for information on how that happened. And then James Webb is going to look for the other big question that I think we all have. Are we alone in the universe? So if we had this talk 20 years ago or so, and you asked, well, are there other planets in other stars? We could say, I think so, I don't think so. We wouldn't know. Since then, we have had a few telescopes, Kepler tests, that were designed to look for planets around other stars, and now we know there are hundreds of them. And this is a popular technique to detect a planet. If I look at a star and I have the light of the star and that star has a planet, when the planet goes in front, the light is going to go down a little bit. So I will say, hey, there is a planet there. Of course, it's easier said. If you think about it, the light is going to dim a very tiny amount. So you need to develop a strong math to say, yes, I see that little change. I see that little change and there is a planet there. So those techniques have been developed and now we have a range of planets. James Webb is going to look for planets, but mainly is going to look at some of the planets we already know and look at their atmosphere. And what we're looking for is, does that atmosphere has water, methane, carbon, things that we know are needed for the life as we know it, and start ruling out how many of the planets that we already know have those conditions. Infrared, this is why we want to look on the infrared. These are the picture of the same part of the sky. This is a part of the sky where we know planets and stars are being formed. They are always formed where you have dust and gas, which means we can detect formation is occurring, but we cannot see it in the visible with our eyes. It's dark. If you look on the infrared, you can detect the heat signature of those objects, and this is what James Webb is designed to do. It doesn't matter what's there. I like to mention it's like in the movies, right? It's night, you don't see anything. The bad guys or the good guys put their glasses and suddenly, you can see the heat. Somebody's walking over there, even if it's behind the house, etc. It's a similar idea for James Webb, to look at the universe on a different way. So James Webb is an international collaboration. So it has a contribution from NASA, obviously, the United States, but it has two instruments coming from the Canadian Space Agency, which is where I started working. And then it has two instruments, MIRI and NIRSPEC, which come from the European Space Agency. So it's an international collaboration. These are all the flight models, the instruments arriving, and this was an incredible moment where they were all put together as precisely as they need to be put for them to be together. And I remember showing this picture to my family in Spain, and they were like, okay, you just put them there together. Hey, there they are. Because it looks messy, but that is not true. They are all precisely where they need to be. If you think this instrument is going to be operating so cold, but we cannot work in those temperatures, so we have to build them at ambient. Knowing, as you know, if you put something in the freezer, is going to change how it looks. So the same happens here, right? I build it at ambient, pointing here, knowing when I make it that call is going to point here. I need to know how to operate it when it's that called. So there is a lot of modeling and a lot of detailed work for many team members to know where everything needs to be. We talked, the instruments, we could talk a lot about them, but we don't have time today, so let's look at the other component, which is the mirrors. This is the clean room at Goddard Space Flight Center. It's one of the largest clean room in the world. And here is a special structure. These are the 18 mirrors. They arrived, each of them built and individually ready. They arrived to Goddard, and another team expert on this put them all together. There they are. They have a cover on top because a clean room is a place where you keep everything really clean before you launch it into space. So a mirror in this direction is kind of the worst thing you can do because anything is going to land on your mirror. So whilst they were being built, you put these particular covers to protect them. And I love this picture, again, very trained. You can see the two team members of this part of the project removing carefully the covers to show what is the most famous, one of the most famous features of James Webb, which are the mirrors. The mirrors are coated, they are made of special material, beryllium. Like all the components on James Webb, they are materials where you try to minimize how much they change when you go cold. And also, we are going to take them cold and warm them and cold and warm them as we test them. So we want them stable. I don't want to go cold and I say, yeah, everything looks great. I warm it up. The next time I go cold, hey, it's pointing over there. No, I mean, you cannot have that. You have to be very repeatable and know precisely what happens. So the mirrors, this material, beryllium, is very good for that. It's also lightweight. But then they have a coating on gold. And if you think about it, the mirrors you have at home are coated in silver, aluminum, because that's what you need to reflect the light that our eyes can see, which is the visible light. James Webb, if we looked on the infrared, our mirrors at home will all be gold. But that's what James Webb needs. So you build a telescope, it's going to be really far, and you have to test it really well because we won't be able to go and fix it. So testing it involves when you launch something into space, which a lot of you, again, know about this. One of the worst parts of the journey is the launch. You're going to go on a rocket that's going to shake what you launch, and it's also going to be really noisy. So it's always very important that you do your vibration and acoustic testing to make sure your payload is going to survive. And to do that, we need to go to special chambers. It means we have to take the telescope from this clean environment, this clean room where we were keeping it clean. And here it is. It's already kind of folded as it's going to be on the rocket, so it can fit. And you can see we put a particular cover over it to protect it whilst it's outside that clean room. So vibration and acoustic, very important when you launch something into space. But then the other important thing is, as we said, duplicate the conditions that your instruments are going to see. So you need to put them in vacuum. And in this case, you need to put them at 40 degrees Kelvin, minus 233. So to do that, we have these big freezers. We have the one at Goddard where we tested the instruments. But once we put the mirrors together, the chamber at Goddard is not big enough, so we had to go to Houston. The chamber at Houston is well known because that's where the testing to go to the moon for the Apollo program happened, so we had to refurbish the chamber. This gives you an idea. This is the front door, and there is another 8 floors. This is how the chamber looks like. This door here covers a portion. You can see here the telescope. So the chamber at Houston allowed us to do something very important, which was to open the full mirrors and do some of the testing we need to do on flight. The instruments are still here on the back. And the rest is, I'm testing it, but I need the stars, right? Otherwise, I won't know what to test. So every time you test, you have a lot of effort on what ground support equipment, things that you need to be able to test what you need to test. So that, again, another big clever part of the team that looks after that. And here is, you can see that same door. Here is the James Webb about to go in. I can tell you, I know they knew they had done all the measurements, but when you were looking at this and the door, you were like, are we going to fit? but it did. I mean, of course, they knew it was going to fit. It went well. We tested for 3 months, 24/7, at the cryo temperatures that we needed to do to confirm everything was working. So the question that comes up is, how do you move such a telescope around? We had to go, here is Goddard, and that's where the instruments and the mirrors arrive. We did the first tests there. Then we have to go to Houston, which is down here. And then after that, there is a part missing still on this telescope, that sun shield that we looked at before, and the spacecraft bus are not there yet. They were being built in parallel in Los Angeles. So we are going to go to Los Angeles. So we have a special container where we fold it the same way that's going to go on the rocket. And you can see here we use a military plane, an A5 that we can open, and then this track goes overnight, right? I mean, it goes very slow, 5 kilometers per hour. You can kind of walk with it. You have to remove the cable. So again, another team, which Pedro mentioned as well. I think going into space is where you mix lots of skills from different fields, which I always tell people, you know, we need mechanics, electronics, software, transport, etc., to make these big telescopes. So whilst we were having all the fun with the instruments and the mirrors, the team at Northrop Grumman, which is one of the contractors in the United States, were having a lot of fun with the sun shield. So the sun shield is a key component of the telescope. It's 5 layers, as big as a tennis court. It's made of a special material again, Kapton. That's very common when you go into space to develop these type of materials that then we end up using on the Earth as well. And you see here the layers. The main purpose is to cool down, to let the telescope cool down, remove any heat from the warm side. So we like to say if you are behind the sun shield, your SPF factor is 1 million. You're not going to get tan ever, ever, ever. You know, just you can be on the beach. And here is us arriving to Northrop Grumman. So here is the mirrors really folded. The instruments are on the back. This is how it will be on a space. And this was in 2018. And here is the sun shield. You cannot quite see it yet. You'll see it a bit more. Here is folded again, as it will be, to be able to go inside the rocket. And it has a protective layer, which is indeed this color, this light pink. And here you can see, to do their testing, they didn't have our component. So they have a model here. They can do their vibration and acoustics, but they need to simulate everything else that's going to be with them. Otherwise, those tests are not important. And here is, a year later, we managed to put it all together, and this is open up, not fully. This is how it will be in space. You can see the side mirrors are still back on this particular picture, and that secondary mirror is folded up to fit in the rocket. So this is a picture of an intermediate test period. So we are almost done there. We finished all the testing there, and we are almost ready to travel to where the launch site is going to be. So the launch site is going to be in the French Guiana. And it's a contribution we are launching on an Ariane 5 rocket, which is, I indicated it was an international collaboration. That's another contribution from the European Space Agency. So Ariane launches from the French Guiana. We are going to go by boat, in this case, through the Panama Canal, which, by the way, charges you per weight, which is something I didn't know, and this is very helpful. So they're very happy that we're going through there. We are about 6,000 kilos, so a good size. And again, you see, this is the same container as before. So the only difference now is that instead of this going inside a plane, it's going to go inside a boat. And travel, it will take about 2 weeks to get there. And here we are. This is the Ariane rocket. So it's always amazing to me how much of the rocket is the fuel to get us out of space. And this is the payload. Here we are on the top. You can see all the mirrors folded. The sun shield is folded here. And then once we launch at the end of this year, we'll start traveling to L2. We are going to take about a month to get there, but then we have another 5 months to do all the other extra operations that we need for the telescope to be ready for normal observations. I'm going to show you a little video to see what's going to happen. Within a few minutes of launch, we start our deployment. So as the telescope, as the travels, we have to start opening it. And we have that, we have, again, a big team where we know exactly what we are doing from the launch for those 6 months. We have it planned minute by minute, so we know what needs to happen. Let me see if this plays. Okay, here. Okay, so this is a few minutes after launch, because you see we don't have the rocket anymore. You saw there how we are getting the antenna that we need to communicate from the ground, and I don't know if you saw it quickly, our solar panel. We have a battery when we launch, but we need to start getting power from the sun as soon as possible. And then you see here, you saw how the sun shield was folded. The 2 pallets are coming down. This starts about day 3 after launch. And in about 3 days, all of this will happen, and they will stretch out. They need to be tensioned, and then we have 5 layers to be able to achieve the heat loss that we need, and they need to be tensioned, and you can see them here. And that happens as we are traveling on our direction. And then this is key the solar panel is key. We cannot operate if our battery runs out. We need the antenna as well as key. We need to be able to communicate. We need the sun shield to allow us to cool down, and then we need the mirrors to come down. Now, the critical mirror is the secondary, because we need the light to be able to bounce to the instruments. If the side panels didn't happen, we have a backup plan to work that way. Once we are in this process, and on this display like this, which will be about 30 days after we launch, then we can start calibrating all the instruments. So James Webb is important from a science point of view, but it's important from an engineering point of view. It's the first time we are launching a deployable telescope into space, and once we demonstrate this capability, other larger telescopes will be able to occur. There is a very important period after all of this is open, which is to align the mirrors. I mean, it's a great idea to have 18 mirrors. When I take my first picture of a star and I look at the image on the ground, I'll have 18 stars, because each mirror is taking a nice picture. So we spent about 2 months moving those stars so they're a single star and making sure it has the right profile. And then after that, we take another 2 or 3 months to calibrate each of the 4 instruments that the James Webb has, and then it's open for science. So I hope you all watch it when we launch, and that you follow us, and thank you for having me.
Okay, can you hear me? I don't know if it's working or not. Okay, perfect. Astonishing. Thank you. Yeah, I think it's gonna be a real game changer, in the way that we understand our origins, let's say, and the way we understand space. And I think it's those kind of accomplishments that you realize how important was after a few years. But anyway, I'm pretty sure that everything is going to be all right. Okay, now we are going to continue with our lineup. Okay, next is Matteo Emanueli. Yes, that's you. He works as a manager of the radar program at Airbus Space and Defense. And he is part of the team contributing to enable the new generations of synthetic aperture radar satellite images. And he also, before joining Airbus, he was working in a company called Conspace. And he was part of, leading some of the most interesting projects in that company. He was building satellite constellations and designing them, and also, just to mention some of the things, between 2018 and 2020, he was chairman of the Space Generation Advisory Council, which is a global non-governmental organization representing young professionals, students, and alumni at the United Nations. So it's a kind of a really important part. So please, the floor is yours, and let me.
Yes, I think you can hear me. Yes.
Okay. Here we go. Perfect. All yours.
P and then, right? Yeah, well, thank you for having me and thank you for inviting me. It's quite a honor to be here, and I'm very happy. This is the first in-person event in more than 2 years, so it's quite an emotion. So today I'm gonna tell you about a specific part of Earth observation, that is Earth observation made with radar, which is basically shooting electromagnetic waves towards an area on the ground in order to get some images. I'm going to give you some brief explanation about it, and then we're going to just dive in all the applications and what you can get out of those data, because of course the second part of the title is more than just images. Hopefully at the end of this presentation you will learn how to use this radar data. Maybe, you know, if you want to buy a house, I know for our generation it might be a bit difficult, but if you want to buy a house, you will know after this presentation how to use radar data to make sure your investment can be safe, let's say. But yeah, let's go forward. Yes. So yeah, I work at Airbus, so we pioneer sustainable aerospace for a safe and united world. This is our mission statement, and I like it because it has some two keywords: sustainable and safe. And with Earth observation, especially with radar Earth observation, you will see how we can make sure that people, so human lives, are kept safe, but as well the environment. And you will see as well how we can monitor human activities and their sustainability. Airbus is a pretty big company, and I work nested in defense and space, connecting intelligence and intelligence. I'm not a spy, though, even if it's intelligence. In intelligence, what we do is basically we have satellites in space, and you will see later some nice pictures. We task those satellites. We acquire data from the ground. We collect data from the ground, downlink those images, process, and then either we start providing those data to our customers, or we further extract information. We analyze those images. And we start creating report and maps in order to create information and as well actionable information, so that our customers and stakeholders can actually act upon the information that we provide to them. How we do that? We have the, I would say, biggest multi-sensor constellation in the world, and is made by optical satellites. And we've just launched the second Pleiad Neo 1 week ago that that has the best commercial resolution down to 30 centimeters, so something like that. So from space, it can see objects that are 30 centimeter large. We have radar satellites. That is the main focus of this presentation. We have partnered as well with Okai 360 in order to provide data from the full range of the RF spectrum, from VHF to the X-band. So wherever, if you have a radio, if you have a radar, those satellites can acquire the signal from space and can provide you a map of this. And in the future, there's going to be more satellite, the CO3D. There's going to be HAPS, high altitude platform that can fly over a certain area and even take videos of those. And of course, the next generation radar satellite, that's what I'm working on. That is going to come later in 2027, hopefully. So basically, so this is the airport, an airport, the Nice airport in Côte d'Azur. So if you want to buy a house in Côte d'Azur, this is what you can get. So from a resolution of 22 meters down to the 30 centimeters of Playa Neo, and actually with a radar constellation we can get down to 25 centimeters. You can see the capability. We can really assess what is happening on ground and the activities, the level of activities, and even recognize object. So we start from the DMC is the constellation that is quite in maybe 22 meters, not so higher resolution, but through spot 6 and 7, vision 1, then Pleiades and Playa Neo, where we have 2 satellites, and soon there's going to be 4 in space. So before moving further on looking at what is or what are the capability of radars, just look at really how this radar satellite work basically. A radar satellite is emitting electromagnetic waves towards a certain area, and from getting from the returning waves is able to, after of course a very complex processing system, to extract images out of the return of this signal. Of course, the radar itself is not that big. I think here you can see a TerraSAR, which is still a big satellite, but 1.4 tons. In order to provide high resolution on ground, we basically exploit orbital mechanics. So, you know, satellites are flying at very high velocity over the above the Earth. So from the moment the first electromagnetic waves is emitted over a certain area, the satellite will fly over the area, and when this wave is then received, the path that the satellite has done flying over the area create the aperture of the antenna, and that's why we call it synthetic aperture radar, because it's not that we have hundreds of kilometers of radar in space. We just fly over a certain target or area of interest, and then we create the synthetic aperture of the radar, and this allows us to have very high and high resolution images of the areas of interest. Why we use radar though? This is an optical image of an airport, and you see there in the red rectangle, that's what happens with optical satellite. There are clouds, atmosphere. So sometimes we cannot really see what is happening just below the clouds. However, with radar, we can. So radar does not need, like optical satellite, sun, the light to illuminate a target. It's bringing the source with itself, the electromagnetic waves, so we can say penetrate clouds, and as well, if the satellite is flying during the night, we would be able to take images also during the night. So it's quite an interesting and flexible system to observe the Earth. What is nice is that so Airbus has currently Airbus and EastSat, there are 3 satellites composing a constellation. The first was launched in 27, TerraSAR X. Then it was joined by a twin satellite, Tandem X, and then another twin satellite that is operated by EastSat, so a Spanish satellite that is PAS. Together, they are composing a constellation that is that has, of course, an increased capacity of acquisition and as well a very high revisit rate. And what is also important is able to take images from the same angle over the same spot at a higher frequency. And this is very important for some of the monitoring application that we will see later, like everything that is connected with interferometric SAR. But I said that this is more than just images, because radar is actually, yes, you can get images, but it's actually a measurement and detection tool. And with radar, we can, getting back to the house that we were discussing, we can monitor the movement of the surface. We can detect changes in vegetation and in the terrain. We can detect vessels over ocean. And we can do, we have created this elevation model, we call it WordM, that is basically a digital copy of the world elevation. And we will get to that and as well the application that we can do with that. I would start with something that is that I work on last year, that is monitor illegal fishing, so detecting vessel. Last year in summer, maybe you remember there was this news about this rogue fleet coming from China, getting close to the Galapagos Island, and well, yeah, starting fishing in an area where they were not supposed to be there. And this fleet happened to came from nowhere, basically. It was not really under excuse me the pun, anyone radar. But anyway, with our partners at OK360, they start getting the signals of the fleet, but they were not able to really distinguish all of them. So we have taken an image, that one with a terracer, and we were able to identify 58 vessels. Down, you can see on the more on the left, you can see all the details we were able to get of the from the ship. Of course, they would not have any identification signal on, but looking at the length and of the ship, the size, and so on, we could or we can imagine what is the role in the fleet. So there were like smaller ships that were sent inside the economic area to fish, where they were not supposed to do it, and then they would come back to the bigger ships, where the let's say the freezer is, and they would deploy or leave all the fishes there, and those fleet would stay, you know, on the sea for many months, and then they would come back to their port, bringing all what they have done. Yeah, maybe back on your table at some point. Something else was, yeah, SEAL Summer 2020 has been quite very there have been a lot during that summer. We monitor the oil spilling in Norilsk, Russia, over the river. So since when there is some patch of oil over the water, it has a different reflection of these electromagnetic waves, and then we were able to monitor how the oil's leak were proceeding over the river. And this is very important, because if we monitor a certain area, we can as well check where this oil's leak has started, and start trying to really providing data to government in order to making sure that this doesn't happen, because of course there's human activities behind, probably not very well checked. Something that happened as well last summer, again, you remember the Mayburg ship that went too close to Mauritius Island, and then there was fuel leak over over the coast, and we were able to really monitor how the the leaked fuel was progressing towards the coast. And this is very important for then the agencies and the people that needs to go then and clean the area, because we can really tell them, look, this part has been affected, or the leaked fuel will arrive towards towards this specific coastal area. You can get there and protect it before it gets polluted. Another very interesting application happened between 2010 and 2012 is connected to change detection. So there was, again, oil contamination. I'm sorry, this presentation is a lot about pollution. In Nigeria, on the delta of the River Niger, and over 2 years, we were able to, and taking images over the area, we were able to notice the change in the backscatter and identify the area where the mangrove forest that was directly influenced by the pollution died. Again, this is not something like we would provide data to agencies in order for to assess the damage and making sure that there can be actions in order to, well, prevent those pollution to happen, but as well act upon and maybe try to mitigate the effect on the ecosystem. Something that is as well very important is monitoring forest degradation and emission. I forgot to say that TerraStar Tandem and Pulse, they are satellite using the X-band, and the X-band, the emission of the X-band does not really go through the canopy of the forest, but it stops just before. But since it stopped just before, we can really assess how, if there is, let's say, if the trees are cut, then we can assess from the difference, from the delta in the height that we receive, we can assess if a tree or a patch of tree has been cut. This is very important because we could monitor the reforestation and as well deforestation. And in the future, with a new generation of satellite, we could go down to the single log. So especially in Europe, that has very high, a very important commitment to reduce greenhouse gases and to making sure that there are enough trees in Europe. This is a very important application. And something that we are doing as well to monitor deforestation, we do it with industry. Ferrero, Lindt, Nestlé, and others. We are monitoring the palm oil plantation and making sure that the suppliers of these big companies, they are not cutting more forest than they are supposed to. Of course, what we do is just providing data to those corporations, but of course, Nestlé had already pledged to blacklist all the suppliers that are cutting more of the equatorial forest than they're supposed to. And this is very important to maintain the ecosystem in those areas. We also look at sustainable agriculture. This you can see over Demmin in Germany. We were able to monitor the harvest of different wheat, barley, or rapeseed, and we were able to, over the span of 6 weeks, to identify where and basically when the harvest has happened. This is very important as well, and with the future satellite, we will look as well. We will be able to look as well to even smaller field in order to monitor all the it's called biological farming that the European Commission is also pushing with the new European Green Deal, and making sure that to provide those information to agencies and government so that everyone knows what a certain area is producing, and what kind of product they can come in order to make sure that there is enough food, because some culture might not be done for food, might be done for something else. But let's get a very important application that can be done is the monitoring of aging infrastructure, which is a problem all over the world. On the right, you can see an analysis that was done for the Brumadinho disaster that happened in Brazil, where the dam collapsed and took the life of many people just below. We were not able to prevent this disaster, but we found out that we took images of the area, and we were able to show the progress and the evolution of the deformation on the area, and showing that actually that this disaster could have been prevented. What has been prevented is on the Mosul Dam. We are able to provide an early warning on what was happening, and these early warnings are very important for dam, because then the pressure and the stress on the dam can be released in order to avoid the accident. I mentioned that this digital elevation model, this is the Sutherland in South Africa, and you can see, and this digital elevation model is produced with two satellites. It's called bistatic, one emitting, the other receiving, and we have covered the entire world with this, so you can actually get a sample from every land in the world at 4-meter resolution. This is very important because if you're buying a house near the coast, for example, this is coming from a project that we have done with the United Nations in Ghana, in Accra. With the rising of the ocean, this might become challenging. And with the World Dam, we were able to create a hydro map and simulate how a flood of 1 meter, 3 meters, or 5 meters would affect a certain area. And this is something very important. I mean, you probably have seen the images this summer, all the flooding in Germany and Belgium. We were able to provide, of course, later, but an analysis of how the flood happened. Let's say if you want to buy a house, you want to know if the river next to you, or how the river next to you is gonna behave in case there are high precipitation, and if your house is in a good position, because I'm telling you, your insurance probably knows, and they will make you pay for that. Finally, erosion, and I chose this part because, I mean, in Denmark, especially in the northern part, I remember there was a lighthouse that was moved of some 100 meters in order to avoid falling into the water. With our surface movement monitoring service, we can over a span of time of different maybe days or months, we can really assess how the erosion is affecting coastal area, but not only coastal area, also mountain areas and so on. And this can really help understanding how the environment where we live is changing, and if your house is in danger or not. So this comes to the end of my presentation, and yeah, I hope now you know how to use how you could use radar data to secure your next investment. Thank you.
Okay, thank you very much. I can see people needs a 2 minutes break. Okay. Let's make 5. Hope you can hear me. We are gonna, please. We are gonna start again after the break. I didn't say anything, but I have a really special admiration for people working on Earth observation. So thank you, Matteo, for your great presentation. And I think it's please keep doing like this. So good, because I think Earth observation is a key technology to fight climate change and to monitor what happens in Earth. So really thank you, and keep doing like this. So now I'm gonna introduce Antonino Salmeri. He is our next panelist. It's gonna be a different topic, still within space, but of course it's gonna be really interesting. He's a space lawyer, specialized in lunar governance and space resource activities. Since 2019, he works as a doctoral researcher at Luxembourg University, and he is also a qualified attorney registered at the Italian bar and holds 3 law degrees, all of them obtained with cum laude. And he is also part of the member of the Space Generation Advisory Council, where he leads the Eagle Action Team on lunar governance. So please, this is all yours.
Thank you.
Everything's okay.
Okay, I can switch with this, right? No? Okay. Oh, okay. Right there? Okay, great. Okay, so welcome everyone. I hope you had a restful break. You're full of energies. So my name is Antonino Salmeri, and today I'm here to talk to you about legal and policy aspects of space resource activities. So as you can see, I'm in a very difficult position here because you heard of amazing space telescopes, you heard about Earth observation and radar, you've seen very interesting presentation with lots of pictures, and here's the lawyer to talk about the boring legal stuff. So apologies for that. I'll try to be as interesting as possible. I have no pictures, so I hope you'll forgive me. And with this, I guess we can start. So we can skip the bio. I mean, Eric was already very kind with his introduction. What I'm gonna talk about today. First of all, I assume not many of you know space law. So what I will do is try to introduce space law for you in a very hopefully understandable way. Then we're gonna talk about space resource activities. I also realized as I was listening to the presentation that I should probably mention what space resource activities are in a few words, because again, not many of you are probably familiar with it. Then I'm gonna leave you with some open questions and recent developments that could hopefully be helpful for the roundtable, because we're gonna talk about, you know, developments in international policy and diplomacy, and this is exactly at the core of my job. So, first of all, what is space law, right? It exists to begin with. There is a corpus of law regulating space activities. It's what we call, because we space lawyers love Latin, corpus juris spatialis, which is essentially a group of customary law, which are provisions that are binding the entire international community by the fact that they have always been adopted. So it's something that happens by means of custom. Then we have 5 treaties, all concluded before, I mean, in the time where we started space activities and then we went on the moon, so between the 50s and the 70s. And then we have a number of UNGA resolution. UNGA stands for United Nations General Assembly, which are more of guidelines that you can imagine on implementing this binding provision. So the binding legal part is the treaties and the custom law. The most important source you have to remember today is the Outer Space Treaty. It's what we call, again, we love Latin, the Magna Carta of space law. It's essentially a treaty on principles, we will go through them in a second, which will tell you the very basic of how do you explore and utilize outer space. So essentially, the purpose of space law, the purpose of the Outer Space Treaty, is to allow amazing people like Begonia and Matteo to do their job, right? To explore space, to utilize it for the benefit of humankind, and in essence, to allow humanity to continue expand. I like to think of space law as an enabler in this regard. So it's a legal regime at the really interaction between law and technology. What we're doing here is trying to also regulate something that doesn't even exist. We imagine that when the treaties have been concluded in the 60s, 70s, nobody had an idea of what we could do with space in practice. You know, we had no idea how far we could go with technology, and still we had to provide rules that would work also for the future. The Outer Space Treaty is from the 1967, but I can tell you it's still, you know, kicking asses, and it's a good treaty because it was done with this forward-thinking approach. The defining features of space law are international cooperation and peaceful uses. I want you also to remember these two concepts because space is big, it's difficult, and it's something that we all share. And again, the founders of international space law knew that very well. And so even though when you think about the development of space, you hear the space race, the competition between United States and the Soviet Union, that is a part of it, but that rhetoric was not into the space law. So when the states sat down at the United Nations to make the rules for space, they were not thinking of a competition, they were not thinking of conflict, they were thinking the opposite. How can we cooperate together in space? How can we ensure that we do not make the mistakes that we have done on Earth in that environment? And how the law can help into that. So that's essential. The problem is that, I mean, not a problem, but the reality is that when space law was developed, it was about states. It was about state activities, big satellites, few activities. Everything was easily controllable. And then companies came in, companies like Airbus, as you've heard. And that changed it, the way we approach space law, because of course certain rules that are fine for a state are not for a company, and vice versa. So one of the challenges of space law today is how do we adapt to the privatization of the space sector, what we call new space movement. And to do that, there's going to be an increasing role of national space legislation to regulate these activities. So the majority of space law is done at the international level, but this is not enough when you're talking about regulating companies, because companies are based on a certain jurisdiction. They have to be regulated at the national level. So we need to understand how we can move space from an international, primarily perspective, to a multi-level governance, which is also the topic of my PhD. So hopefully I'll find out how to do that. So the fundamentals of space law, those are the rules that apply to all activities, no matter exactly what you're doing. So you can be doing the James Webb Space Telescope, or you can be doing radar observation from space. These rules apply to you in any case. The first one is the most important. It's the golden rule of space is that it is free. Free for everyone, every state to be precise, to explore and use. So this is a fundamental principle. If you think about it, it should not be taken for granted because, for instance, the rules governing the airspace, which is just below space, are the opposite. It's sovereignty. Each state decides whatever they want to do. They own it. They do whatever. Space is different. It's free. It means that we all have to share it, that we have to be mindful of each other in space. To protect the freedom of outer space, Article 2, it's another fundamental principle. It says nobody can appropriate it. No state can go, and this was especially important. Imagine this was 1967, and the United States and the Soviet Union were in a competition to go to the moon. But none of them thought, I'm going to the moon, I'm going to put a flag, and this will be mine. You know, the desire could have been there, but they didn't think about it. They said the opposite. We want a rule that says whoever arrives there first doesn't own anything. This will still remain open for everybody to be explored and used for the benefit of humankind. So that's a really forward-thinking approach if you think about it. And again, looking at how we behave on Earth, it was not taken for granted that we have managed to keep this principle in space. But we do, and it's one of the most important ones. To ensure that these rules will be upheld, we also said that international law in general and the UN Charter are applicable in space. This is a fundamental provision because sometimes you may hear that space is like the far west, or you may hear people like Elon Musk saying that Mars is a free planet outside any jurisdiction. That is not true. International law applies in space, and the reason is that we want to protect space. We want to protect space as an environment where the rule of law still continues. So the obligation you have on Earth will also be relevant when you do space. You cannot go to space and escape your international obligation or the rule of law. Space is fully subject to that. Continuing into this line of direction, there are the peaceful purposes of space. Again, as I said before, peace was one of the main objectives of space law, and still is. There was also another fear of the superpowers. It's like, let's not put nuclear weapons in space, right? That they imagine in the 60s, this was the real danger of a nuclear war. If somebody could put a weapon, a nuclear weapon orbiting space, it could have the power to destroy the entire world at any time with catastrophic consequences. So they said, let's not do that. And there are different rules. I'm not going to go into details, but there are different rules on using orbit, because orbit is a more strategic environment that could be used for certain military purposes. So not to do war in space, but for instance, to use the satellites that Matteo described before to support military operation. And this happens every day. Huh? So with satellite images and radar communication, we know exactly where to hit a target. So this is military uses of space that is very clearly allowed under space law, because of the strategic value of the orbit. But there are limits, so you can use it to support, but you should not shoot a laser to each other in space or put any nuclear weapon. Celestial bodies are a different story. They are bound by the exclusively peaceful purposes, and we will see that when we'll talk about space resources. And then there are a bunch of other provisions which say that essentially every time there is an activity in space, a state is responsible for it, meaning that if something goes wrong, it will be that state that will pay the consequences of it. Then a state will be liable, and it's not the same. I am Italian, and in the Italian language, we don't have the legal distinction between responsibility and liability. Most of you are from Spain, so you probably don't have the same. But in English and in legal English, responsibility means bearing the consequence of something. Liability means that you will pay for those consequences. So this is a critical difference. The responsible state and the liable state are not always the same, because the responsible state is identified based on the jurisdiction. Who has jurisdiction on a certain activity? The liable state is the launching state. So for instance, the James Webb Telescope will be launched from French Guiana. That means that France will be liable for any damage that eventually could happen because of the James Webb Telescope or during the launch. And that is even though France has nothing to do individually with that, simply because they're the launching state. And then the responsible state will probably be the United States, because it's the one that is exercising jurisdiction over the scientists that operate the telescope. And then this is also had to do with registration and formally acknowledging that you are exercising certain control over an activity or an object. And then Article 9 is a final provision I will mention you today. It's a fundamental provision. It's what I call the systemic key of space law. It puts states in front of each other, and it says that whatever you're doing with space, you have to do it with due regard. This has to do with the fact that space is free for exploration and use. And as you very well know, our freedom ends where the others begin. And the same is in space. If everybody would be free to do exactly whatever they want, then nobody could exercise space. Everything would be threatened because the limit would be absolute. So due regard means, yes, you're free, but keep in mind that there are others with the same or different interest, and you have to be mindful. And if there is any problem, you have to consult. And this is what Article 9 says. And finally, there are some provisions on environmental protection of space, which we could definitely do better. And so that's going to be an area that we will try to improve at least. Now, before I go into the implications of this principle on space resource activities, I want to spend a few minutes on what space resource activities are. You have heard about presentation mentioning what we call space application, or let's say space exploration into a more scientific sense, but again from Earth. Space resource have to do with space exploration and deep space exploration and the expansion of the human civilization in outer space. What is the critical role of space resource is that through space resources we can reduce the cost and increase our effectiveness when we operate on other celestial body. So please don't think about space resources as something, let's go to mine an asteroid, take gold and bring it back. That's not economically or scientifically very feasible. It's super expensive and very complicated, also unnecessary if you think about it. But what we want to do with space resources is, let's say we're going to go on the moon. And you probably heard that many countries now want to go on the moon and explore it and have a sustainable presence. Now, if you have to bring everything with you, everything you need from Earth, it's going to be not feasible. Again, as you heard before, the majority of a rocket is fuel. And the problem is that to bring stuff in space, we have to have a lot of fuel and we spend money. And so if you have to bring tons of materials with you, you're not going to be sustainable exploring space. You're just going to spend a lot of money and your abilities will be reduced. So space resources are there to help us. So when we go on the moon, we don't need to bring the oxygen, the water, the materials with us. We use what's on the moon. And there is a lot of ice, for instance, there we discovered that we can use to then make water, to then make oxygen breathable for the astronauts. We use the regolith to build infrastructure. We don't have to bring everything with us. So that's the critical role of space resources. They're going to be a fundamental component of a new type of exploration, which is less expensive and more sustained and sustainable. The issue is, how do we regulate that? Because, of course, space resources are a very critical and topical subject in international space diplomacy because they are in any ways limited. And so the question becomes, if we are all free to explore and utilize space, if space is to be used for the benefit of all humankind, then how come you can go and exploit a resource individually, right? How come is this not national appropriation? And there are many questions that I will point out at the end. So the very first question that actually happened when we thought about utilizing space resources in space exploration was, is this legal? Can you do it, right? Because as I said, there is a principle that says you cannot appropriate space. The question is, yes, it is legal because you have the freedom to utilize space. And the freedom of utilizing celestial body essentially means that you can make use of the resources that are there. So yes, you can do it. And no, the non-appropriation principle does not apply to space resources, and we will see what is the legal difference. However, the freedom to utilize space and to utilize celestial bodies is not absolute. As I said, there are many limits to consider. The most important ones being the fact that you have to share the benefits of space activities, including space resource activities, that this has to remain what we call the province of humankind. So it's an activity that should not be only for the rich or the powerful, but should be for everybody and should be done, you know, with the interest and benefits of all countries in mind. And the fact that celestial bodies shall remain accessible to every actor that wants to go and explore them. So yes, you can do space resources. No, it does not constitute appropriation. Why? Because the non-appropriation principle was meant to avoid that the state would expand its sovereign control in space. So it does mean that you cannot go to the moon and have another part of the United States on the moon or the Soviet Union. That means that that is not possible. But at the same time, when you go on the moon and you extract a resource and you separate it from the celestial body, then you can appropriate it. But the fact that the territory where you're operating will still remain not yours. It will still remain not under your exclusive control, meaning that you will have to share it. To do that, of course, it is fundamental that all the actors in space resource activities will respect international law and will not threaten international peace and security. Because again, we do space for peace, not for war. And that it goes into the fact that space resources shall be used for exclusively peaceful purposes. This is a fundamental principle because you probably have already heard that there are, let's say, corps in certain countries like the United States, the Space Force, and this kind of military rhetoric. We can talk about it in another occasion or during a break, how much of that is really true and how much is just rhetoric. But the important thing is that you cannot, legally speaking, take the resources of space and use them in military application. So that is a fundamental difference between exploring space in orbit and exploring it on a celestial body. You cannot take the resources on the moon and use them for military purposes. That is prohibited. So the application of space resources are limited to civilian application, commerce, science, business, anything you can imagine, but not military. Other further implications are more into the legal side, so I'll be brief on those. Essentially, that means that the licensing state will be responsible for the space resource activity that it licenses. At the same time, there will be launching states liable for the damage caused. There's going to be a registration state to exercise jurisdiction and control to make sure that all the rules are respected by the individuals. And all of these states will have to pay due regard to each other. Meaning that, again, they cannot behave as if they are the only one there. They have to be mindful of what can happen in the future and how their own operation is impacting the ability of others to conduct similar or different operation. And those states have to consult with each other if there could be interferences. And I can tell you there can be many of them. Imagine that, for instance, if you're mining the south pole of the moon to get ice, and then a starship is landing close to your operation, your entire activity will be blown up. Because landing on the moon, for instance, is an activity that creates a lot of interference. There is a lot of dust generation. There is a lot of shaking the surface. So if Elon Musk will just go and land, or Jeff Bezos for what it's worth, and doesn't tell you that it's coming, or does not consult about it, and come close to your area of operation, you can just give up and you're going to lose all the results. So states will have to consult and prevent these interferences to happen by means of diplomatic consultation, and then in the future, mediation and arbitration if there is any conflict. To do that, there is critical process which is about information sharing. If states that intend to do activities, and especially space resource activities, inform the UN of the nature, location, duration, and result of the activities, we can already avoid the main problems at the beginning. This is a provision that I didn't mention before. It's Article 11 of the Aerospace Treaty. I didn't mention it because it has never been used, essentially. This provision says that states agree to share information. Now, as a lawyer, I will tell you that when a state agree to do something, it means it's not bound by this. It says that I'm very kind, so I will do it, but if today I don't want to do it, you can do nothing about it. And so that's why Article 11 has never been used much. There's been 20 submissions over the last 60 years under Article 11. Because states didn't see the value in sharing the information. At this point, though, I'm one of the advocates saying that we should change our mindset and use this provision because it's helpful, because you realize that sharing information is in your own interest to prevent interferences. Now, there are many open questions related to space resource activities, and those are the key ones. I'm not gonna answer those because, of course, this is exactly what we're trying to do today and eventually in my work and with other organizations. But you have to imagine that we really have to think about many things and re-challenge the way we understand space law and international law and the interaction between public and private activities. And the most important one for me is still to guarantee the peaceful and sustainable uses of celestial bodies like the moon. They're precious to humanity, and so we don't want to screw them up, right? So this is, for me, it's the one that we need to answer. We don't want conflict on the moon, and we want the moon to stay utilizable for future generation. So this is also at the core of the activities I do for Space Generation Advisory Council, is that we as the next generation of space explorers, we want to have a say in how these are utilized, because we're going to be the one inheriting the consequences of that. And I have to say, the space community, differently than the Earth one, is much more open to this kind of discussions. Finally, this is just an overview of the recent policy developments that you may want to look at. The first one is the Hague International Space Resources Governance Working Group. That's a very long name. This was a very nice experiment. It was a multi-stakeholder consortium created in 2015, operating for 4 years, and creating what we call building blocks. These building blocks are essentially the fundamental things that we need to keep in mind when regulating space resources. And so the work of the Hague Working Group has been critical for the international discussions we're having today. The evolution of the Hague Space Resources Working Group is a global expert group on sustainable lunar activities, which is specifically focused on how do we explore and utilize the moon, including its resources, but not just limited to that. And so this is what I'm trying also to do with Space Generation Advisory Council. The EAGLE team that Erin mentioned before stands for Effective and Adaptive Governance for a Lunar Ecosystem. So we're a group of 14 young professionals advocating for the sustainable use of the moon, and we developed a report that we essentially complement the Hague Space Resources Working Group and the Global Expert Group. And then there is also another entity called the Open Lunar Foundation. They organize a series of webinars called the Moon Dialogues. I would encourage you to look at them on the internet, which are meant to bring this policy discussion to the general public, as we're doing today, and get feedback and cross-contamination among different fields. The 4 flags that you see there, and I'm about to end because I promised to be brief and I didn't make my promise, so apologies to Henry for that. These are the 4 states, the only 4 in the world, that enacted national legislation for space resources. So the United States was the first in 2015. Then Luxembourg followed, 2017. That's why they're paying my PhD. They're interested in that. Then Japan, very recently, and then the United Arab Emirates. Those 2 over the last 2 years. Finally, these are what we call unilateral approach. So this is what the United States government will do to regulate this at the national level. At the same time, we need to also coordinate this regulation to make sure that we can avoid tensions. And so this is done at the regional level by documents like the Artemis Accords or the International Lunar Research Station. Those 2 are 2 programs for the exploration of the moon. One involves mostly Western countries. The Artemis Accords is United States and partners like ESA, Japan, all the countries you see there essentially. And then the International Lunar Research Station is a project initiated by China and Russia, and they're looking for international partners as well. Both these programs will be regulated by certain documents, which are meant to provide coordination among the partners. But the most important part, sorry, I think the computer blocked here, okay. The most important part here is that we need to think different, right? The idea is really that these problems are innovative, and so to solve these problems, we have to be innovative as well, And so creative solutions are needed, and those cannot come only from the law. They need to come from a multidisciplinary approach. And so here you can see some of the examples that we are thinking to propose, but they can only come if we integrate the legal and policy development with the technology, with the economics, in order to understand that this is not something that a single expert can solve. We need a group of people from different backgrounds and different entities. And this is what the United Nations is working on. Right as we're speaking, there are meetings of a newly created working group on space resources that was created a couple of months ago, and it's meeting for the first time as we speak today during the plenary meeting of the United Nations Committee on the Peaceful Uses of Space. And so this working group just started, and on a 5-year plan will try to come up with principles that can ensure that space resource activities are done in compliance with space law. So in conclusion, this is a quote from a very famous man, Roosevelt, and the idea is really that to get something you never had, you must do something you never did. Sorry, it was Thomas Jefferson. And so in principle, space resource activities are permitted. We have the legal framework to do that, but we have never done it. So we need to create and to be evolving also from the legal perspective in order to do something that indeed we have never done. And to that, multilateral, multi-stakeholder, and multidisciplinary debate is the key. We need to involve everybody, also people not from the space field. So that's why I'm very happy to be here today, because indeed we need those type of cross-contamination. I think success or failure will depend on our ability to innovate and renovate. We still have time to succeed, but it is time to act. And so I'm very happy to continue this discussion. And I would like to thank you for your attention.
Thank you. Okay. Okay. What about now? Yes. Okay. Here we go. Thank you very much, Antonino. Really interesting. Sometimes we focus so much on putting things out there in space, and we really forget about regulation. It's really necessary. And especially in these days that we are living like a new era for space, I think space policy is going to be like a really interesting topic. Thank you so much. And now, last but not least, we will have Jose Merallo. He's a professor at DTU Space. He leads the magnetometry group. Maybe you will explain it better, but in plain English, it's how we measure magnetic fields from space, isn't it? And then he focuses on these measurements of magnetic quantities in space, and most of the most important models of magnetic fields in space, they have been developed by his group, and he is also he has been collaborating with the main space agencies, ESA, NASA, and some others, and also some of the most important space players in space industry. So please welcome Jose Merallo.
Yeah, thank you very much. I'm honored to be here and able to present my work or part of the work, and I will start with. Oh, how do you do it in Mac? I'm not Mac user. Please.
I can help with that.
Oh, of course, I have to press this slide. Okay, great.
Okay.
Oh, yes, it came. So first of all, yeah, I'm employed or working at the Technical University of Denmark. It is just 15 kilometers north from here. So the local speaker here today. I think also for the next sessions, but anyway, the Technical University of Denmark, it was actually founded by Hans Christian Ørsted, and if you remember him, maybe some of you don't remember. Actually, it is the person who discovered electromagnetism for just 201 years ago. So. Of course, there was a lot of events organized last year, but everything was cancelled, just like you mentioned this morning, Paula. We just try to promote the idea that what will happen, what you don't think will happen if electromagnetism was not discovered, right? I mean, what would be the world like? So just think about it. So actually, he has this quotation that the agreement of this law, and now it's not a legal law, but it's a physical law. with nature will be better seen by the repetition of experiments than by a long explanation. And I will come back to that in a little while. Then, yeah, I have been in the university the last, time flies, 29 years. I did my master's in Spain in the University Complutense of Madrid, and then moved to Oviedo. And in this group was collaborating with DTU, and then they offered me to come to DTU to just exchange 1 year, and then you see what happens. So time flies. Then I started to be involved in some measurement of the magnetic field, and then just what I will tell you about. When I was looking at the other speakers before me, I was thinking, okay, what I would do about my presentation, because in our group, actually, we have delivered flight hardware to more than 100 missions in the last 30 years. So I just can pick up whatever I want, and I wouldn't talk about astrophysics because we have extreme experts here in the group, or remote sensing because now we have Matteo. Of course, law I don't know anything about. I try to follow it. so I try to put this one first. Now I have seen part of this picture this morning. Then Begoña presented a picture of the sky with the stars. Then I think it was Paula presented the potential event in Norway next year. It was So for us Spaniards, looking at that, we never seen that in Spain. This nothing happened. These auroras. So for the northern countries, this is more common, especially in the northern Norway and northern Sweden. So can you imagine people in the old days being there and looking at that? This is the art of gods, right? Okay, I tried to take you to a journey about some places in our solar system, because the topic of space instrumentation is used many places, but since we have different experts here, I will try to give you some about space instrumentation on Earth, which is our home, on Mars, on Jupiter, and then I will take you to Psyche. And I hope the journey I'm bringing you is going to be within the regulation laws that Antonino just presented. So, yeah, first of all, let me introduce you to, well, actually, it doesn't have introduction, this one, Perseverance. I mean, now I tell you the citation from Ørsted. I mean, keep going, keep doing experiments, and what the name that the Mars 2020 rover got, Perseverance. Keep going, keep trying, just move on. This is the scientist's idea from us to keep going, to trying to investigate, to research, to be thinking out of the box, etc. This is the way that actually this rover is being. So there was a lot of news, hot news in 2020. We were invited to the launch in KFC, but it was cancelled. Not the launch, but the presence of all these VIPs and us, well, the scientists. And then it was landed this year. And this, of course, is not going to be the biggest event this year, because we know that the James Webb Space Telescope is going to be not yet bigger later this year. So the mission lifetime of this rover is about 1 Martian year, which is 2 Earth years. And this is a JPL that basically drives these Mars missions. So from this mission, we have been contributing from DTU Space. Well, actually, basically, to start with, we have a lot of contributions from many places. In this rover, there's actually a Spanish contribution. It's an experiment which is measuring the atmosphere or atmospheric parameters of Mars, wind and temperatures and things like this. It's based on the Centro de Astrobiología in Andalucía. And then there's also contributions from Norway and then Holland. And of course, also from DTU, we have also a contribution. In this case, we are participating in the pixel instrument, the one here, in the robotic arm, which is called, our contribution is the context camera for this experiment. And then the reason of doing that is because, of course, if you know, Perseverance is, the main objective is to try to find out whether we can find life. Of course, we know that we want to see only life in another planet somewhere else. Now, Begoña told us about these exoplanets somewhere else. But then here we have the opportunity to see whether we can in situ determine whether there is life or not. So the experiment that we are participating in consists of a X-ray source, just the one that you are using in the dentist. Let's put your teeth and look what it starts. And of course, looking at the rest of fossil remains. And then the way it works, we have this X-ray source, and then we have the camera here. Oh, sorry, I just jumped too much. The camera here, that it will, of course, with X-ray, will take some pictures in the X-ray band, and then with the camera, we have take some pictures, and then we are illuminating in different colors, and with different colors we can determine different structure in the different bands in these pictures. These pictures are about 2 centimeters by 1 centimeter, 3 centimeters by 1, very small ones, and then you can see this is the visible picture. But if you take the picture in different bands, you actually see another structures that will tell you whether there is a remainings of other material fossils. And the ones of interest is these ones that are the trital parite and solidification, where will tell you whether maybe there was potential life. And this method was developed by a Australian called Abigail Allwood. One paper published this paper is the PI of this instrument, and she's of course working on JPL, but originally she's from Australia because she was investigating, this as a geologist investigating these kind of things in Australia. So now, but the problem is that, what is not life on Mars? Well, sorry. We don't know yet. We're actually trying to see the answer. Actually, also, our instrument is going to find out which of these samples can be collected, and then later on there will be another mission that picks up these samples and brings them to Earth. And here is also another potential problem, because we don't want to bring any alien life into Earth. So this one will happen in space in a extremely secure kind of laboratory before the samples can be analyzed on the ground. So but the problem is on Mars. If you look at Mars, if you remind the picture of Mars, that it's a red planet. It's just dry and it's red, right? So the thing is that, of course, because of all the studies also made by remote sensing pictures like the ones that Airbus is doing, there has been missions that have taken a picture of the landscape and then determined that actually there's erosion, and therefore there must be having water and stuff like that. Also, we have measured water on Mars. So why is Mars doesn't have an atmosphere? So they actually the hypothesis at the moment is that at some point Mars had a magnetic field, but because it lost its magnetic field, then all the atmosphere was blown out by the sun. If you think of Earth, here we have a little tiny, of course this is just this is not a scale, as you can imagine. This is 150 million of kilometers. And then we have the Earth here, and then we have the sun, and the sun is just an enormous body that is constantly, is kind of a nuclear reactor, constantly sending particles all the time. What we call it the solar wind. So when we have the Earth here, we have the magnetic field of the Earth, but because of the interaction, if we didn't have the solar wind, the magnetic field of the Earth will be a kind of symmetric structure. Because of the solar wind, it pushes the magnetic field towards the sun side of the Earth, and then makes this cavity, which is enormous on the other side of that. So now they may be here that sometimes the sun has some spots, some black spots, and in that case, it's like the sun is erupting some clouds of plasma, which is high energetic particles. And these things, I mean, since the sun is not stable, it's constantly doing something. Once in a while, we get actually one of these bursts into the Earth, and that makes that actually the magnetic field of the Earth will be trying to protect us from that. It's working as a magnetic shield towards the Earth. If now the magnetic field disappear, then we'll have complete exposure to the actual solar wind, which is not a nice environment for any kind of life. So that's the maybe reason why Mars looks like today as it does, because of that. So in this situation where you have the daily evolution of the sun, you can see that how the Earth reacts, or the magnetic field of the Earth reacts to this constant daily. Of course, we have some daily variations because the alignment of the rotation of the Earth and on the magnetic field are not the same. And then you have also this burst of sun constantly going on, and therefore you have this structure, and you can see that the sun is, or the magnetic field is protecting us from that. And once in a while, when these effects are extreme, then we call it a magnetic storm. All the particles that are coming here are disturbed, or are sort of the trajectory are changed, so they follow the magnetic field lines of the magnetic field of the Earth, and then they come into these polar areas, and that actually what is still to the aurora we observe on the northern or southern hemisphere on the Earth. So the magnetic field means something for life. So, but the magnetic field of the Earth has different sources. So the most dominant is the one we observe, which is about 95% of the source of the magnetic field we observe. Is generated in the core of the Earth. It's about 3,000 kilometers of radius. If you imagine the Earth is about 6.2 thousand kilometers in radius, but only half of that is where we have this core where the magnetic field is created. And this magnetic field is about 60 plus minus 60,000 ounces. This is the quantity. Just remember this quantity about. And then today the magnetic field looks like this. I mean, we have, as you see here, we have a larger in the equator. We have about 30, and the direction is horizontal. But on the poles, we say a symmetric type of model. Then we will be coming down on the northern part, and then coming out on the southern part. It's like it's a dipole field, we call it. So, because of this, we want to investigate what happens with the magnetic field, and we know that the magnetic field of the Earth has changed over time. I mean, actually, we call it some inversions of the magnetic field. That suddenly the magnetic field was not like this, but actually the north pole of the north pole of the magnetic field is on the south pole, and vice versa today. But in the old days, there has been actually been swapped, and then this happens once in a while. I actually have records on the continental borders that actually this happens maybe every 100,000 years. So we want to understand why the magnetic field will change shape and also direction. And of course, because this is important for the life on Earth, also make some consequences what will happen in the future. So because of the magnetic field, we are able to actually, it's kind of a, if we may say, X-ray of the internal part of the structure of the magnetic field. We can do it with these observations. So, but in order to do that, we have to first model the large field, and then we have other contributions which are due to other effects. I don't know if this is animation. No, it's not working. Okay, it's fine. Then when we have removed the large contribution of the magnetic field, we have other contributions. We have the magnetosphere, which is due to this cavity that I told you just about before. And then when we can also model that one. Then when we remove that one, then we can have some ionosphere currents, which are in a height of about 100 kilometers, and you can see these ones are driven by the sun. Well, you could see it if this is supposed to be moving, but now we take it from this where. And then when we remove these magnetospheric currents, we have the ionospheric currents, and then look at the magnitude. We come back from the previous slide from 60,000 to 61 is 1,000 factor, and then we go to another factor here of 30, and then we remove that because we now understand how this is, and then we take the actual crustal field, which is in the surface of the Earth, which is about of 10 nanoteslas, and then at the end we have also some, because of the moon, the water, the tidal waves are changing, and actually this also creates a magnetic field which is on the order of 2. So we're going from 60,000 to 1 nanotesla. How do we do that? We want to measure this magnetic field from the space, and then that's the reason why we want to do this. Is that because if we have observatories all the way in our planet, then you can see that these observatories, these dots are not well uniformly distributed over the Earth. So if we had a satellite during the day, we have this location over the globe. And then we have this on the night, and then you have the satellite. I mean, you have the Earth that is rotating. You will have an inertial satellite orbiting around the Earth, and once the Earth is rotating, this will be scanning completely the magnetic field. This is just in one day. You will have 13 orbits, but in many years we'll have basically very, very dense coverage of all that. So the observation of the magnetic field started by NASA in the 60s with these missions. It was only scalar, and then they made a vector, MaxSat, and then there was 20 years without any dedicated spacecraft, and then when there was Ørsted, the DTU basically started this project. Then we have scalar and vector, and that's actually what started participation on that one. Then we have the different satellites, CHAMP, SAC-C, and today we have SWARM, which is an ESA satellite from the Earth Observation Program, which is dedicated exclusively to measure the magnetic field of the Earth. Consists of 3 satellites in a constellation of about 500 kilometers, 2 of them flying in parallel, and the other one perpendicular in that orbit, such that we can actually make some stereographic measurement of the magnetic field. So we have delivered the main instrument on the spacecraft, which is the vector field magnetometer, which measures the 3 components of the magnetic field, and it measures very precisely, but we need star trackers to tell where the magnetic field is pointing to with respect to a local reference frame located on the Earth. We see that means that if we make a measurement, say that component is pointing north or west or down or whatever, and then also we have built the star tracker system to provide the alignment to this one. The challenge of this star tracker system that was also developed for the previous satellites is that it has to be non-magnetic, because we don't want to measure magnetism for any component of the spacecraft. That's why we have this boom here. Usually, I will show you another picture later. Usually, this boom will be put on the body of the spacecraft, and after launch the boom will release. And this is just one mechanism compared to the James Webb Telescope that will be these peanuts, but it's still very critical. So yeah, we're at a distance of about 3 meters from the spacecraft, and then at the top of the boom we have an absolute magnetometer, which gives us the reference. So just in details how this optical range, this is the optical range covered by thermal shields, because we want to have very stable temperature, because we're measuring very precise, and with the materials we're using are very specifically designed to this purpose, but still have some drifts and some that we want to control. So this is sitting an optical range that is made out of carbon fiber, very stable, and you can see here that the requirement for the instrument is to measure the range of the magnetic field 65,000 nanoteslas with an accuracy of 0.25 with a pointing accuracy of 1 arcsecond. So what is that? I mean, imagine a golf ball and a distance of 10 kilometers, and then the angle that you will see in this ball actually is 1 arcsecond. So it's very small angles. And if you think of the accuracy that we're talking about here, imagine that you want to measure 1 kilometer with 1 millimeter of accuracy. So this is a quite stringent requirement. So usually what we do is that we get some raw measurements, and we apply this it's the only equation I have here. Hopefully it's very simple. It's just we have the raw measurements. We take the offset, which is a constant, and then we apply some sensitivity. This converts from some units to the actual units of nanotesla, which are physical units, and then we get some rotation with related to the star tracker and to star tracker, and then we get the field components in nanotesla in the right orientation. So we're using GPS, the star tracker, and ASN, this scalar magnetometer, for reference in the time, inertial, or nanotesla. So we have to calibrate that. I mean, we know that it will work. We are testing a lot of things. We calibrate that, and then we bring it to an astronomical facility. In this case, I mean, since I'm coming from Spain, I travel some contact in Almeria, Calarto Observatory, nice place, nice city, actually. And then we go there, but the problem is that, when I say I'm going to Spain to the south, to Almeria, how lucky you are. Yes. The thing is that now I'm showing the picture here during the day, but of course, as you see, it's a star tracker, we need to observe the stars. So we have to do it at night. So yes, we do the installation during the day, and then we do the observations during the night, and then the nights are very long, right? And then when you come back to sleep, then you are very tired. And then usually it's 3 days in a row, because you have to take the night that is available, that is star clear to make observations. And then we calibrate. We have the optical bench here, and then we have the sensor and the sat trackers, and then we establish the orientation, relative orientation between the two systems here. It's a very complex test. So, yeah, just as Begoña was saying that, we now, you can see the booms are placed together to the spacecraft here. They are released, the 3 from the launcher. The launcher is the most exciting theme for a lot of, we have to make a big event. And then launch loads, we have to make a lot of work before to ensure that this will work. The temperature, then we have to ensure that it will work at all temperatures. A vacuum, we have to ensure that we don't have, we can get off the rid of the heat, or it doesn't get too cold and so on. EMC, we don't want to get interference. So there's a lot of constraints. Radiation, we're going out of space, and radiation becomes a problem. Radiation is high energetic particles can destroy your electronics. And then in this case, it's an operation satellite. It has to produce data, so we need to ensure that everything is delivering data all the time. So we try to avoid glitches and things like this. So we have to react very quickly if something happens to resolve the anomaly if any case happens. So there is a lot of things going on, but system is running today and very good. So we are very happy with the results. So now we're going to Jupiter, because Jupiter has also a magnetic field, if you know. Jupiter is a big planet. And then the thing with Jupiter is that the magnetic field is 20 times larger than on Earth. So that gives us an opportunity to analyze what happens in a larger planet with that. So this mission, Juno, is a NASA mission, also with JPL and Goddard Space Flight Center for the instrument. I will here. We have a large spacecraft. This is a spacecraft that is about 4 tons, launched in 2011, and took 5 years to come all the way to Jupiter. And at the moment, it's operating. We are on the 35 flyby. It's making flybys of the magnetic field of the Jupiter every 40 days. And then here we have large solar panels. And earlier, this is the first spacecraft that went deep space with only solar energy. So that's why these solar panels, early on, it has been some RTGs which uses some nuclear radioactive elements. So this is solely based on solar energy. And then at the top of this bomb, this is about 13, 14 meters of longitude. And then they're also deployed when it's being sent in space. Then we have the boom here, where we have the experiment. Of course, there's all experiments in spacecraft, but I was only talking about the magnetometer. But there's imagers and gravity experiment and also atmospheric experiments and so on. But in this case, we're sitting there because we want to be also away from the spacecraft, not to be disturbed with that. And then we have the first Perijou 1 in 2016, and at the moment we are on the 35th, as mentioned. Actually, the last one we passed by also the Ganymede moon in the one of the Galilean moons. So early on there has been other probes from about Jupiter which came farther away, and from that some constraints on the magnetic field was determined, and this is what we call BIP Model 4. And then you see the first flyby of Juno. Actually, because of the model was developed based on data from that's long away, it's not as detailed as the one from Juno, which suddenly already in the first orbit of flyby, we got a field that it was on the order of 8 Gs that we have never observed such a large field ever before. This is the flyby, with so close we are to the planet here with Juno. Based on the first 8 orbits, we make and you can see here also the orbits are more or less equidistant, and then we were able to build a model of the planet that is fairly precise. And then one thing that show up is this peculiar spot here. It's not the red spot, which is atmospheric and winds and so on, as we see in the pictures from Jupiter. This is a magnetic spot. And then if we look into the more in that, what happens here is that you have a magnetic field of Jupiter that is extremely complex. And then based on the observations we have performed is that, because one of the objectives of this experiment, which PI is in Goddard Space Flight Center, is do we have a core, is a solid core or not, like on Earth? And then one of the things that has been discovered is that the dynamo of Jupiter is much closer to the surface than on Earth. But then another thing that has been found out is that actually we have field ejecting from the North Pole and coming out in the Southern Pole. But actually, we have also some effect here. Actually, it's a 3-pole magnetic field. On Earth, we have 2 poles. In Jupiter, we have 3 poles, and that's very strange. So it's very complex. So this has been published also in some journal. And then finally, I will tell you to Psyche. Psyche is the last object in the solar system of this journey. I will bring you to about. This is an asteroid that is in between Mars and Jupiter. So actually going from Mars to Earth, and now to Jupiter, and then back to Psyche. This is a mission that NASA has been planning, and it has been a very one of the problems, or one of the challenges with the Psyche is that we have only a window of 6 weeks for launch to arrive in 2026. So the launch is fixed in exactly 1 year from now. And then the arrival will be in 2026. So there is no anticipation for any delays. So people, it has been closed down also at JPL and everywhere else in GTU and so on. So here we have been working very hard to get that. We have just delivered the 2 instruments. This is 2 magnetometers from GTU. In addition to a GRNS, is a gamma ray neutral spectrometer and an imager for Johns Hopkins University and ASU, Arizona State University, which is the PI of the mission. And then we are collaborating with the MIT is actually the PI on the instrument magnetometer. We deliver the hardware, and they are doing the science together with us. So, and the way of the objective of Psyche, it is the name of the asteroid is called Psyche, but also the mission is called Psyche. Is that it's an object of 200 kilometers in diameter, which may be made of metal, maybe actually a missing planet in between Mars and Jupiter, and of course this will tell us yet more about the origin of the solar system. And then if we discover that, of course, actually some pictures have been taken by the Hubble telescope saying that maybe it has some composition, we have to in situ or closer by make a spacecraft or send a spacecraft that actually will investigate even further how Psyche is made of. And that's why we have a magnetometer on board. So the reason why is that if it was to be a planet, of course we'll start with a hot core here, solid core, and then it will have a magnetic field, and then during 4.5 billion years it will solidify, it will be cooled down, and then it will make some more detailed features of the magnetic field, and that's why we want to measure and then find out whether it is a Earth-like core or not. So this is one of the objectives of this mission. So now talking about law again, asteroids. It's an asteroid. We have this in situ reutilization of asteroids and so on. What is it worth? And of course now, of course, this is just of course journalists. They like to say, okay, now we have that object. It's metal. It has some raw materials. How much will it cost? How much can we earn from that? And since from the Hubble Space Telescope they say, well, you have here something like made of iron and nickel, then some say, okay, it could be worth 10,000 quadrillion dollars. And this is what some media publish. That's all. And this, you just try to put zeros. How many zeros is this? Is about 10 times 10 to the 18th. If you look at the TEMA gross domestic product in 2020, maybe this is the one I could got. This is 0.0, 10 to the 12. You take the Spanish one is 3 times more. You take the US one is about 20 times more. So, but if you look at the zeros, this is 6 orders of magnitude larger than these two. So yeah, I mean, is it worth it to bring it back to Earth? But of course, this doesn't take into account how much effort or how much technology has to be developed to bring it back. But I mean, I just leave it there. This is not my business. Just I wanted to show you that interesting stuff that people is looking in that. And I think that was the last part of my talk.
Okay. Thank you very much for the presentation. It was really interesting. Unfortunately, we ran out of time, so it's now time for lunch. Okay, I think we all are also pretty interested in that. If you have also any question that you would like to address to our amazing panelists, you can address them directly to them at some point during the rest of the event. We still would like to maybe rearrange a bit the program to squeeze them and try to do some short roundtable maybe later in the afternoon. But let's see. In any case, this was an amazing panel. Thank you all. And it's time for a break.